introduction. Hi, everyone. Let's jump right into talking about instrumental variables regression. So the outline I'll follow today is we'll recall endogeneity, we'll introduce instrumental variables regression. I'll talk about the intuition and then talk about regression, talk about the ways to assess instrument validity, and I'll discuss implementation using one simple example, and then I'll go through some more examples and summarize. A common aim for health services research is the estimation of a causal effect. So we're interested in what is the effect of treatment on some outcome. Ideally, we'd estimate this effect using a randomized control trial. However, conducting a randomized control trial is not often feasible. So an alternative is to perform regression analysis using observational data. To estimate the causal effect of treatment on outcome, there must not be any unobserved variables that are driving the outcome. That is, treatment should be exogenous. So recall a linear regression model where Y is the outcome variable of interest, X is the explanatory variable of interest or treatment, E is the error term. E contains all other factors besides X here that determine the value of Y. Often the parameter of interest is beta 1, where beta 1 represents the change in Y associated with a unit change in X or in treatment. And in order for beta 1 hat to be an unbiased estimate of the causal effect of X on Y, X must be exogenous. So just recalling what exogeneity means here is conditional mean of the error term given xi equals 0, meaning that any additional info in the error term does not help us better predict y. Xi and ei are considered correlated when there is omitted variable bias, sample selection, or simultaneous causality. And if xi and ei are correlated, then X is considered endogenous, which would make beta 1 hat biased. Here's where instrumental variables come in. When X or treatment is not exogenous, another method is necessary for estimating the causal effect of X or treatment on Y. And one possibility is using instrumental variables regression here. So I'll give you a little bit of intuition of the IV regression. So recall our linear model, recall that, so we're gonna assume that the X is endogenous. And what we wanna do is think of this X as having, the variation in X as having two components. One component is correlated with the error term, which is what causes endogeneity and it's problematic. This other component of the variation in X is uncorrelated with the error term, or is the exogenous variation. An instrumental variable is a variable that uses only the exogenous variation in X to estimate beta 1. So essentially, we want to isolate the exogenous variation in X that is uncorrelated with the error. So we want to think of X over here, and we strain out the problematic part of X that's correlated with the error term, and the part that remains is the part of X which is uncorrelated with the error term. So showing it to you in a diagram here. So recall that we talked about X as having two components. There's a part of X that's correlated with the error term that's problematic, and there's a part that's uncorrelated with the error term. So an instrumental variable is a variable that can capture only this exogenous variation in X and get us the part of X that's uncorrelated with the error term. Often we have to look for the instrumental variable, and that is usually the hardest part of implementing instrumental variables in research, looking for this Z or instrumental variable. The other thing that we want to note here is that Z should not directly influence Y, or Z should not itself be correlated with the error term. Here, Z can be used to isolate the exogenous variation in X. Since Z itself is exogenous, its correlation with X is exogenous. So what we do here is to get the clean part of X, we use this correlation of Z and X, which is exogenous, and we use this component of X, this clean component of X, to study the impact of X on Y. So how do we do this? Oh, I'm sorry. Let me go over, I think I skipped some slides here. Yeah, so how do we do this using regression? How do we get this clean component of X that we want? We can conduct two-stage least squares regression. And essentially, it's two consecutive OLS regressions. In the first stage, you'll regress X on the instruments, Z in this case, and you'll get the uncorrelated part of X, the part of X that's uncorrelated with the error term, and this is the part that's correlated with the error term. If you just predict or get the predicted values of X, that'll give you the uncorrelated part of X that you want, the clean part of X. And then you would regress Y on this predicted X. This predicted X comes from the correlation of X with Z. You regress Y on X hat, and this gives you the beta 1 two-stage least squares estimator. Note that X hat is uncorrelated with the error term from the original regression model, and beta 1 hat will be an unbiased estimate of beta 1. Since we conducted two regressions here, we'll need to correct standard errors. This IV regression can generalize to the case of more than one endogenous regressor. So if we had K endogenous regressors, X1 through Xk, and exogenous variables, W1 through WR, you would need M instrumental variables such that M is greater than or equal to K, implying that each endogenous regressor should have at least one instrument. It can have more than one. So how do we identify a valid instrument? There are two conditions. We've generally already talked about them in the intuition, but I'll just formalize them here. The first condition is instrument relevance, which is that the instrument Z should be correlated with X, that it should have an impact. And this is important because if Z was not correlated with X, it wouldn't be able to pick up the component of X, the clean component of X, this exogenous variation that we're wanting. So it definitely should be linked here so it can pick up that correlation is what we're going to use to study the impact of X on Y. So if there's a weak correlation here, that would not be good. We wouldn't be able to get reliable estimates. The other thing that we've talked about is the instrument not impacting the outcome variable directly. This is just saying that the instrument should be exogenous. So Z does not affect Y except through Z's correlation with X. So the only impact that Z can have on Y is through this channel, this green channel, which is through the impact, an indirect impact through the endogenous regressor. Okay, sorry. Here we go. So if the first condition is violated, the first condition of relevance is violated, we would say that the instruments are weak. Instruments that explain little variation in X are considered weak. IV regression with weak instruments will provide unreliable estimates. We can test for weak instruments using a rule of thumb. We can regress X on Z, and if the F statistic is greater than 10, we would indicate that instruments are not weak. This is just a rule of thumb. In general, we still need a convincing argument that the instrument is relevant or strong. If there's a violation of condition 2, exogeneity, we would end up with endogenous instruments. Instruments that are correlated with the error term are endogenous. IV regression with endogenous instruments provides unreliable estimates. And unlike condition 2, where we could do a statistical test, here this condition can't be formally tested. So we definitely need a convincing argument that instruments are exogenous anytime that we're using instrumental variables. I'll walk through an implementation example here. It's a very simple example, and I'll be showing this implementation example in Stata. In this case, we're interested in looking at the impact of education on wage using experience as a control variable. First, we'll use a baseline OLS estimation without using instrumental variables. And here in Stata, what we would do is we would say regress wage on education and experience. And we would look at the coefficient on education, which is the coefficient we're interested in, and we would look at the t-statistic to see if it's statistically significant. And that's how we would do a baseline OLS estimation. However, we're concerned that education may be endogenous, and a person's innate ability could be driving both their education and their wages. And education, I should say here that education here is measured in years of education, and this is the hourly wage. And so we're concerned that education is endogenous, and so beta 1 hat will be biased. So recall our intuition and how we want to think about the endogeneity problem. So consider using an instrumental variable, the number of siblings. Number of siblings is being used here to instrument for education. And so the relevance assumption that we're making here is that siblings are correlated with the number of years of education, in the sense that parents with more kids cannot provide a high level of education for each of them. But to the extent that we think that ability is what's driving endogeneity and ability is innate, we wouldn't think that the number of siblings, having more number of siblings makes you more or less able. So number of siblings should not be directly influencing wage. And so for now, we'll just assume that these conditions hold so that I can show you the implementation. But in general, and in the next examples, we'll be discussing whether the assumptions that are being made are reasonable or not. But here I just want to show you how to implement this in a statistical software such as Stata. So what we would do here is, like I said, here I'm going to show you how to run this example, run the IV regression using two different OLSs. So here we've got the first stage regression, where we regress education on experience and SIBS. And what we want to do here is look at the reason why we regress on education, experience, and SIBS is because experience is an exogenous variable, so we'll typically include it. It's considered, it's technically instrumenting for itself, and SIBS is instrumenting for the education. So this is regressing the endogenous regressor on the instruments in the first stage. And what we want to look at is the SIBS variable and see if the SIBS variable looks statistically significant. And the t-statistic is pretty high. And if the coefficient is in the direction that we would expect, which is that a higher number of siblings tends to reduce the years of education for an individual in this example. And so so we do see that the instrumental variable that we're using here is relevant. And so what we would do here is use the predict command and name a variable, educat in this case, using the option X, B, and theta. So this is going to give us the predicted values of education from this first stage model. And so essentially, this is that clean component of X that we wanted. And we're now going to use this clean component of X that has the exogenous variation captured from the instrumental variable, and we're going to put this in the main regression. And so this is the second stage of the two-stage least squares regression, where we regress wage on EduCat instead of an education and an experience. And here we get our coefficient that we're interested in, but note that the standard errors are incorrect here because we ran two consecutive separate OLS estimations, but haven't yet corrected for the standard errors. But what I want to show you here is that this coefficient is 139. And what we had gotten in our baseline model was a baseline OLS model when we had not considered the selection problem, the endogeneity problem. We were getting a 76 on the coefficient. So using the IV approach does often change the coefficient here. Now I'll show you how to conduct this in theta using just one step. So if you were to use IV regress to SLS, and then put in the dependent variable, put in the exogenous variable of interest, and in parentheses, you would put in the endogenous variable, excuse me, equaling the instrumental variable. So this is how you would specify the commands, and then you would get a coefficient on the education variable, which is the exact same coefficient that we got when we conducted two separate OLS estimations. However, the standard errors are slightly different when we do it using this command in one step. So the standard error here is 28.0, and here the standard error was 28.28, but the coefficient is exactly the same. I've left here some more YouTube videos that will help show you the implementation procedure. So the example that I just went through, Sebastian Y goes through in more detail here and shows how you can test for endogeneity, and Chuck Huber shows built-in tests and theta, testing for endogeneity and first stage statistics, and Annie Kachova shows how to run the IV regression in SAS. So you can try those out. What I want to focus on for the rest of the talk here is more IV regression examples, as they'll help us understand IVs more illustratively. They'll help us better assess the quality of the IV. And for determining the quality of the IV, we want to look at or discuss raised critiques of assumptions that are being made about the two IV validity conditions, IV relevance and exogeneity. So this is kind of the key component of using IVs, really knowing how the IV relevance assumption is being applied, how the IV exogeneity assumption is being applied, and if you're going to do research using instrumental variables, it's very important to make sure that you're arguing your points soundly on these two fronts. And the examples that I go through, I encourage you to revisit these example papers later to look for ways that authors may have addressed some of the critiques that we will raise here. So the first example is looking at the impact of intensive treatment versus regular treatment for AMI patients, and the outcome is whether or not AMI patients end up dying. So what I typically do is list out, when I look at any instrumental variables paper, I list out these items, and so we'll do this for the next few examples that I've got. The outcome here is death among elderly patients with acute myocardial infarction or heart attack. And the treatment we're looking at is intensive treatment versus regular treatment. So the endogeneity concern here is that factors that are difficult to observe, such as comorbid diseases, severity of illness, complex details of a patient's health status, and patient-physician preferences could be influencing both intensive treatment and mortality. So these factors could be, in your error term, making the intensive treatment variable endogenous. So the authors use as instrument distance to alternative hospitals minus the distance to nearest hospital. So an alternative hospital is where patients could get intensive treatment. The relevance assumption that authors are making here is that patients with lower differential distance to alternative hospitals are more likely to undergo intensive treatment. And the exogeneity assumption that's being made here is differential distance has no impact on mortality directly. So looking at our picture here, we're saying that, again, the relevance is that the distance to alternative hospital relative to nearest hospital does have an impact on intensive treatment, meaning that patients that live closer to the alternative hospital are more likely to get intensive treatment, and that this differential distance doesn't have a direct impact on mortality, and that the only impact it has on mortality is through this indirect channel of impacting the endogenous regressor first. So the paper uses this table 1 to highlight the endogeneity concerns that we just talked about. They split up their sample into people that did not undergo catheterization over here and people that did undergo catheterization within 90 days of an AMI over here. And what they highlight here is that that at least using the observed variables, not being able to comment on unobserved variables, but at least using the observed variables, we see that people that did not undergo catheterization tend to be slightly older and have more comorbidities or are sicker, which would mean that we're selecting in, catheterization is selecting in potentially younger or healthier patients, which would overestimate the benefits of catheterization, potentially. So in this table 4, the authors consider the exogeneity and relevance of using distance as an IV in their scenario. And keep in mind that the exogeneity criterion can't be tested directly, but there are ways that we can hint at it, and that's what this paper is doing here using this table 4. So now the paper splits up the sample into 2 groups: people that live relatively close to the alternative hospitals, so where they have a lower differential distance, and people that have a higher differential distance over here. So this table shows that the distance seems relatively independent of the comorbid characteristics of patients, in that these comorbid characteristics seem similar across the two distance groups. And then they try to establish the relevance of this instrument by showing that the likelihood of getting treatment does differ based on distance. So we see here that people that live relatively close to the alternative hospitals are more often getting the intensive treatment, and people that live relatively far are less often getting the intensive treatment. So this establishes the relevance of this distance variable, or doesn't establish it, but hints at it using this table. And then they conduct the 2-stage least squares estimation. Now, they also present, the paper presents their result without accounting for selection bias. So they estimate the cumulative effect of catheterization on mortality post AMI. So like they look at 1 year post AMI here, and show that the decrease in mortality is negative 30.5 percentage points. They adjust for demographic and comorbid differences and show that this effect reduces slightly. However, when instrumental variables are used, the cumulative effect of catheterization is much smaller. It's negative 4.8 percentage points. And so this just highlights what the paper had already predicted or hypothesized, was that if we didn't account for the selection bias, the effect would be overstated because healthier and younger patients are selecting into more intensive treatment. And so when we control for that selection, that the effect is much lower. So there is a reduction in mortality, but it's much smaller. So I'll go through these next examples a little quicker, so we have time for questions. In this next example, the authors are interested in looking at the impact of early life hunger on late life health. So the outcome here is health in later life. Treatment is health hunger in early life. And the endogeneity concern here is that later life outcomes and early life conditions in parents' households jointly depend on unobservable confounders. So the instrument the authors use here is the exposure to a famine in early life. And the relevance assumption that's being made here is that famine during early life increases hunger in utero or at ages 0 to 4. And the exogeneity assumption that's being made here is that famines do not impact health in later life except through hunger in early life. So looking at our picture here, again, the relevance assumption that's being made here is that famine in early life does impact early life hunger, but famine in early life does not have any direct impact on late life health, except through this indirect channel of famine in early life impacting the endogenous regressor and then impacting late life health. So I like this paper because it positions itself in the famine literature. So prior studies had looked at the impact of famine on late life health. So they would use a famine indicator to look at health. But this literature argues that really what we're doing is we want to look at the impact of hunger on health through the effect of famine. So, and the famine doesn't affect everybody. So getting the nutritional status of the individual would get us the impact of hunger on the people that actually do get impacted by the famine. So the paper hypothesizes that that if they were just to look at the famine as an indicator and not as an instrumental variable, they would get a smaller effect because famine is not necessarily increasing hunger for everybody, but that it's only increasing the hunger for some individuals, and that's really what we want to capture here. And that is what they end up showing. The paper shows that the estimate, the causal effect of hunger exceeds the famine effects by at least a factor of 3. In this next example, authors are interested in looking at the impact of doctors' advice to quit smoking on patients' behavior to quit smoking. So the outcome of interest here is smoking cessation. The treatment is provider advice to quit smoking. The endogeneity concern here is that providers may be more likely to advise heavier smokers and or those who've already been diagnosed with smoking-related conditions. So the heavy smoking habits of an individual are something that may be observable to the doctor, but not observable to the researcher, and they're therefore in this error term because the heavy smoking, like if a patient has heavy smoking tendencies, then it will make it harder for them to quit. And so that's something in the error term that isn't controlled for, that's correlated with potentially doctor's advice. And so that's the endogeneity concern here. The author's instrument for this endogenous variable using provider advice to diet or to exercise. And this is essentially supposed to capture a measure of provider tendency to advise. The relevance assumption that's being made here is that provider advice to diet or exercise is correlated with the advice to quit smoking, but that provider advice for diet, nutrition, and for physical activity are not directly impacting patients to quit smoking. So again, looking at our diagram here, we're saying, the authors are saying that the relevance of this instrument is that the advice to diet or exercise does impact whether or not the same provider gives advice to quit smoking, but that this advice to diet or exercise doesn't directly have an impact on patients quitting smoking. The paper discusses a few different ways in which this this assumption may not hold, and they walk through how they address some of those concerns. So one such concern would be if individuals are health-minded and they choose physicians that would give advice on diet or exercise. So that would mean that health-mindedness of individuals is something that's in the error term that would impact their likelihood to quit smoking, because we would think that people that are health-minded may be more motivated to quit smoking. But if they're also picking doctors that are more likely to give advice on diet and exercise, then our instrument would be correlated with something in the error term, which is health-mindedness of the individuals. And so the instrument would no longer be exogenous, and so that's the problem that that's one of the problems that the paper discusses. This next example. Oh, and I should tell you that what they find here is that provider advice did lead to a 7.8 percentage point higher quit rate after selection is accounted for. Now, this next example, the authors are interested in looking at the impact of retirement on health. So the outcome is health, treatment is retirement, and the endogeneity concern is that declines in health can compel people to retire. So the authors are interested here in retirement's impact on health, but really health could be impacting retirement decisions. So it's difficult to disentangle such simultaneous causal effects. So the instrument that authors use here is the self-reported probability of working past ages 62 and 65 when individuals were employed. The relevance assumption that's being made here is that people who indicate high probability of working past these milestone ages are less likely to retire. And the exogeneity assumption that's being made here is that after controlling for hereditary health trends and past health history, self-reported probability captures the preference to retire and not an individual's health-related expectation to retire. So this exogeneity assumption is really, like, I want to clarify what's going on here, is that the authors control for hereditary health trends and past health history. And they say that after controlling for these trends, these variables, which is what you'd think that individuals base their health health-related expectations of retirement on, that once they've controlled this away, those health-related expectations in this instrumental variable are no longer there. And then this instrumental variable only captures preferences to retire or expectations to retire that are non-health related. Because if they were health related, it would be components that are health related in the error term that would make our instrumental variable endogenous. Okay, so let's look at our picture so I can highlight that again. The relevance assumption that's being made here is that self-reported probability of working past age 62 or 65, which are milestone retirement ages, does have an impact on retirement. And the self-reported probability of working past age 62 or 65 does not have a direct impact on health after controlling for these health history and hereditary health trends. Now, what they find in this paper is that IV estimates end up switching the sign when compared to baseline OLS estimates, and that retirement exerts a beneficial influence on health changes. Here are some other IV examples, and I encourage you to take a look at these examples and work through them in the way that we just worked through these other examples. So to summarize, IV regression is a powerful tool for estimating causal effects. Conditions for a valid instrument are relevance and exogeneity, where relevance implies that the instrument must affect treatment. The exogeneity assumption is that the instrument must be uncorrelated with all other unobserved factors that may affect outcomes. And using invalid, weak or endogenous instruments will give meaningless results. So the hardest part really to using instrumental variables is finding a good and convincing IV. These examples and other examples can help us get better at identifying potential instruments and assessing the validity of IVs, and being able to argue the validity of our own IVs when we do use them. Some tests are available to check instrument validity, but what is absolutely necessary is a good story for why an instrument is relevant and exogenous. And that's all I had. So I'll take any questions at this point. It looks like we have some time.
That sounds great, Kritee. Appreciate it so much. There are, you kept me busy in the chat. So I think I answered some of them, but I'm gonna pose these because it's never clear to me if everybody sees the answers or if it's just the person who asked it. Some of the questions I think are relevant. So in the education sibling example that you gave earlier, where siblings were the instrument, education was regressed on experience along with siblings and turned out to be statistically significant. Is it appropriate to use it again in the second stage, or does that introduce bias?
It does not belong in the second stage because siblings does not directly predict. So here, let's walk through that real quick. Sorry, I have to find my slides real quick. So you don't want to put, so siblings is an instrument, right? So you regress, you use it in the first stage regression, but we're making the argument, by definition, the instrument should not affect Y. So it doesn't belong in that second stage equation at all. So we do not want to put that in there.
Great, thank you. You stress this issue that the IV should not be associated with the outcome, and you highlight that here. And you mentioned, which I agreed with, is that often intuition is called on, and people have to spend a fair amount of time when they're writing their papers proving their intuition. One of the attendees asked a question, why not just use something simple like R squared? And if your instrument increases R squared at all, wouldn't that then fail your assumption here that it's not correlated?
So you would.
So sorry to be more, you could use a regression with your variables and include your instrument with and without your instrument. And if the with instrument increases your R squared to fit on the outcome, it tells you your instrument is not.
Well, I think, yeah, thank you. I understand now. So the R squared will increase when you put in additional variables, period. So you want to show that the specific instrument has an impact. So you want to look at the t-statistic on that specific instrument.
Great, thank you. There was a request, and I don't know if you know offhand, where there was interest in understanding examples or good examples with multiple IVs. So here you've not only hit the jackpot and you found one IV, but jackpot and you found multiple IVs. And
yeah.
Do you have any examples in the literature where you think that they're really good about those?
Yeah, so the example that I provided with this one right here, this is actually two IVs that I, for illustration purposes, just combined into one. So there's actually two survey questions that have been used here: provider advice to diet and provider advice to exercise. So there's two different IVs that were used in this paper. So we already have an example here that folks might want to look at.
Great, thank you, Kritee. I was so busy answering questions, I think I missed that example. Talk about over-identification tests in that example.
So there is this concern that if you have too many IVs, that the additional IV will be could be correlated with the error term, and so you can conduct some over-identification tests. And they're actually I provide those links that show you how to conduct them. But often you're going to be struggling to find one IV. So I think it's uncommon to have many IVs. That's just something to keep in mind. But there are some tests in Stata that you could run.
Right. And then here's a very general philosophical question for you. Are there ways that you think about testing IVs prior to using them? Sort of the conceptual thinking about what would be a good IV before you start going through the mechanics of testing it.
Sorry, so is the question, do I think about it before I,
no,
or are there ways that I test it?
Are there ways that you think about it when you're considering a possible IV to continue down that road to say, I want to test this IV, or when someone suggests to you that this is a potential IV, you dismiss it out of hand? And it goes into that thinking.
Yeah, so I know that Liam Rose in his seminar on regression discontinuity had also referred to this book by Scott Cunningham, Causal Inference Mixtape book. And in that book, I like that Scott says good instruments should feel weird. So really, like, siblings to me feels a little bit weird of an instrument. And the reason why good instruments feel weird, you want to think kind of outside the box. Is because if you're too within the box, the problem is that, like, whatever endogenous variable you're looking at, and you're looking at the impact of this variable on the outcome variable. If you stay too close to these variables, you're not going to be able to find an IV that doesn't also impact this variable. So you really have to kind of step outside the box to find an IV. So you want to be constantly thinking of things that are correlated with this with an X, but won't impact the Y.
Can you repeat the name of that book by Scott Cunningham?
Yeah, it's called Causal Inference Mixtape.
Thank you so much. There was a question about that.
Yeah, I think we should quote him saying, good instruments should feel weird. I feel like that's a good thing to remember.
Right. Have you ever, in your experience, used instrumental variables after a randomized trial?
I have not. No.
So we have, and I'll just highlight this because it is an area that people don't typically think of. So typically a randomized trial is testing people who are in one treatment or another treatment. And the treatment effect that you get is just the sort of the average from being assigned to one group versus another group. Behavioral trials typically, excuse me, you have this problem of crossover. In both groups, you can have people who are not adhering to treatment or implicitly join the other treatment by doing things that outside of being assigned to it. So there has been this desire to do what's called on-treatment analyses, which is to say, what happens if we're really interested in using this clinical trial and just say, what about the people who took the treatment versus didn't take the treatment? In that analysis, if you pool your data from both arms, you're implicitly getting back into this problem of having this bias. And people, the treatment assignment, knowing that that changes your propensity to be exogenously assigned to one of the treatments as a way of teasing those things apart. But I only raise that because there's a lot of trials that happen in VA. And if you're a VA researcher, often you're working alongside people who are running trials, and you could say, that's a really interesting question. Have you thought about it from a slightly different perspective? And we can get a different estimate that might be much more interesting to the clinical audience or policy audience.
Yeah, that's great.
Trying to see if there are any other questions that are coming in. This Q&A is hard because they just keep flooding in.
I don't know if that's a good thing or a bad thing.
Can you speak to a model where, and it's an area I think you know, where X is service-connected disability and Y is people's earnings? So this is a very VBA or benefits question, and the homogeneity problem that we're struggling with when we think about earnings or earnings losses and their service connection. One of the questions, getting back to, and I think you know the paper by Meistis, and Meistis uses the rater as an instrumental variable. But Meistis is not alone in using sort of raters. Joe Doyle at MIT has done similar things with ambulance drivers. Can you speak a little bit about the intuition behind that model?
Yeah, so the idea there is actually similar to what we're talking about here in this example, where we're using someone's propensity to, like a rater's propensities to score or to be more lenient or to be more strict as a way of figuring out where whether the service-connected disability would be higher or lower. So we would think that raters that tend to be more lenient are going to give higher ratings, and that could be one. So that's the instrument there, the leniency or the strictness of the rater that's being used to impact to look at the impact of service-connected disability on wages here. And so we would think that the propensity to be more lenient or strict by the rater doesn't directly impact the Y or the wage of that individual. So that's why that's a good idea.
Great, thank you. I love that you gave the example of the McClellan piece from the mid-90s. Can you speak to, and I can help if you don't know as much on this sort of travel or distance as an IV? People have used it in much broader settings, and does that give you nerves or concerns when people are using that same IV elsewhere?
Yeah, I mean, I think that with every IV, you have to look at the details, and so you really have to sit with the IV papers and see if you're convinced. So, for example, distance to ED would be different than distance to primary care. And so you want to think about whether it makes sense to use distance to ED in a setting. So distance to ED might be something people can't predict as easily. And so they're not, so it's going to end up being more exogenous. But I think that in general, you want to think about the specific situation and work through whether you're convinced on this framework.
Yeah, that's great. I was thinking the same thing, because I've seen people say, well, because McClellan did it, we can use it. But if the context of McClellan's paper was that these were people who had a heart attack, and essentially the ambulance, because it was an emergent condition, was taking them to the closest hospital, and then they were able to understand sort of the equipment and sort of the intensity of care at those different hospitals. But if it's a very different situation to think about distance when the person's chronically ill and sort of their diabetes, because one, they might move, two, they might change their insurer to reflect the service set of the kinds of things that they really value, which again would invalidate that instrument. Here's a question that just popped up. Is it feasible to use instrumental variables in administrative data, claims data alone? In VA, we have access to information on clinical, but not all administrative data have clinical information. And do you have any experience with just administrative data in IVs?
I don't. I can't see, I don't see any particular restrictions to using an IV using different data sets. I'm not seeing the problem, but so I think it's just about getting creative and thinking outside the box. Todd, do you have any leanings on that?
Yeah, so the immediate ones that jump to mind are questions where they're using geography and time to understand the effects that would not be relevant in a different geography in a different time. So the classic examples of this would be state taxes for tobacco as a potential instrument. There's an even better one that was published, I think it was last year, where they were using extreme distances in traffic in LA. So, you know, you're driving along and in LA and there's a traffic incident that causes huge backups. And those huge backups lead to road rage that they then translate into domestic violence. So in that case, the instrument is, you know, it's spatial information on traffic information that's specific to where the person is and the claim of the domestic violence. So again, you're thinking out of the box. So it's a great idea that you were suggesting, Kritee. Now, for the person with the administrative data, they might have to do additional linking to get that time information. Yeah. So, and then there's a question that come up. There's a joke that it's easier to find a Loch Ness Monster or Yeti than a good instrumental variable. And then they said it can be difficult. The real question is, can you discuss the interpretation of the second stage coefficients? My rough understanding is that it's the effect of the marginal case. Yeah, so I didn't want to get into this too much here and I wanted to keep more introductory level here, but there is this concept of local average treatment effect versus average treatment effect. So in the case where you would expect heterogeneous effects of treatment on the outcome variable, in that case, the instrument will only identify the causal effect for the group that takes up that for whom there is a correlation between Z and X. So you're only identifying a causal effect for people for whom there is an effect of Z and X, meaning that, like, if let's say that in this scenario it was only men, that it was only for providers that were men that ended up giving advice on diet, that also gave advice on quitting smoking, then the causal effect that we would be identifying here would be
for patients that saw male providers.
Great answer. I also just wanted to highlight, I loved your example, Kritee, of the coffee grounds and the coffee as a way through this idea of a projection matrix. Because I remember in econometrics, they're jumping into this projection matrix, and you're trying to think of what's the visual. So that's a great visual. There was a question that came up about sort of, is there a priori knowledge about the implicit bias in before you use instrumental variables, before you remove the grounds? Do you always know that instrumental variables will attenuate the difference or expand the effect size, or is it completely, is the biased estimate could be biased in any direction?
You do typically know what will happen. So for example, in this case, so you do tend to know what will, you may not know what's exactly going to happen in the first stage, but you know what's going to happen in the second stage. So you will have a prediction. So for example, in the McClellan paper, we expected that because we were seeing that healthier and younger patients were typically more likely to get to undergo catheterization, that we would see a larger effect or larger benefit of catheterization if we didn't account for that selection. And when we do account for that selection, we would expect that this beneficial effect would reduce because we're accounting for that selection problem. And we do see here that once authors account for that that selection problem, the estimate changes substantially. So you should have a hypothesis on what you expect would happen. And it was the same thing with the famine example, where the authors predicted that that compared to the famine literature, where we were just looking at the effect of famine on health, that effect was going to be lower than if we looked at the used famine as an instrumental variable impacting hunger, because then we would capture the effect of hunger and people that were actually affected by the famine. And so that effect would be larger than if we had just put in a famine indicator.
Great, thank you. I think we are almost at the top of the hour. That's the last of the questions that have come in so far. I'll hold out for another 20 seconds to see if there's anything else. But if not, I just wanted to thank you, Kritee, for a great presentation.
Yeah, thank you, Todd. And thanks everyone for the questions and engagement. If you have other questions, feel free to email me.